Okay. So a lot of juicy stuff here. What we know so far is that solids can be crystalline or amorphic. Is that correct? And there are other categories if you're really into it. Do you notice? Do you remember they said that some crystals are long-range repeating patterns, aren't they? Maybe throughout the entire material, it's the same pattern. Whereas amorphic solids might have little pockets of patterns, but then really not the same pattern all the way through. So I think God was pretty smart to say, you're going to need some things like this. You're going to need things that are crystalline, and they're strong, but some crystals are incredibly strong. Remember the aerogel, though. The aerogel is kind of like pretty brittle, wasn't it? But then also, God made some other materials that didn't really have that super structure to them, and then they can be molded, like plastics and rubber. Those amorphic things, like that. So we actually need all those materials, don't we? Yeah, go ahead, Clay.
Is putty a liquid?
Okay, and we can have a great discussion. I just don't want to do that today, but glass, putty, if you hang a piece of putty right here, slowly it flows like a liquid. Some people would call it a liquid. Some people call it a amorphous solid. Putty is really neat also. This is not in your chapter. I'm not sure why you didn't put this in here, but putty is one of those materials, when you put a force on it gently, it'll stretch. But take that same piece of silly putty, go like this. It snaps. And that's called a non-Newtonian fluid. That's another word you could use. I've seen people do that. They take a bowl and they put starch in it and water. Starch and water. It's like soup, like that. And if you make it just right, okay, you say, what do you think's going to happen if I do that with my hand? You would think, oh, it's going to go all over the place like water would. But it doesn't. When you hit it, the stress in there makes it rigid. So if you become an engineer, you will have many more categories for solids than that. Glass. Is glass a really slow-moving liquid? Over time, will glass actually migrate, because of gravity, downwards? I've read several articles on there. Some people say yes. Some people say no. When I was your age, somebody taught me that if you went to a house that was like 100 years old, and you look in the glass in there, that the bottom of the glass is always thicker than the top. That proved that in 100 years' time, the glass would flow and it accumulated bigger in the bottom. But then I read another article, and they said that the only companies who made glass back then, they made it with a spinning method. And the spinning method itself made more glass end up at one end than the other. So I don't know the exact answer there. Is glass flowing? Is it a super cooled liquid? Is that what it is? So those are great questions you had. Anyway, the second thing we showed yesterday was some people say piezoelectric or piezoelectric effect. Do you understand that? There's some crystals, that when you put a force on them, when you put pressure on them, they will actually give off an electric charge. Is that correct?
Yeah.
Okay, now, yes, I'm sorry.
So why wouldn't we take advantage of that and, like, besides just its small productions, like, make it industrialize it to, like, is it like such little voltage it's not worth?
I think there are some. I don't know everything about different companies, but if you want to look up some companies, say, is somebody taking advantage of that right now? Is there a business that runs essentially on piezoelectric effect? And I think they if it works, I think I would. The one thing I thought was neat about it is if you put the mechanical force on it, you can make electricity. That's good. And then we can do things like light a lighter. We can do lots of things. But I like the reverse. What if you provide electricity? If you provide electricity to those crystals, what do? Instead of I put a force, make electricity, what if you put electricity on those crystals, what do they provide? A force. And what you can do with a force is you can make movement, can't you? And so he made a speaker. And what about a watch, a quartz watch? What's that? There's a crystal there, and it has a battery. And the battery provides electricity to the quartz watch, and that quartz starts moving. And it moves so precisely that it moves. It's the best timekeeping thing we've ever made. It moves exactly at 32,000 something times per second. And that's a pretty good timepiece there. Yes?
Why is it that when you apply force to the two crystals that they give off a current?
That's the video we watched yesterday.
Yeah, that's right. But the video, that's right. And you could rewatch yesterday's class video. But if there's a certain kind of arrangement of atoms, okay? Remember what happened when they squeezed it? Okay, I don't want to tell the whole story, but certain atoms, when you put them next to each other, the word's called electronegativity. They will tend to pull electrons away from other atoms better than others. And so they said some of those atoms have a slight negative charge and some have a slight positive. And when they're in the right formation, they cancel each other out. But when you squeeze them, the net positive charge ends up being near the top of that pattern and the net negative here. And so if you can attach a wire between the positive and negative, you can produce a spark or electricity. My battery, the reason this battery works is there's a chemical reaction here, and it produces a place where there's excess electrons in one place and a deficit of electrons in another. So if I were to make a complete circuit with this battery, the electrons would tend to go from negative to positive. And same thing with that piezoelectric. If I can make a positive negative charge, a voltage difference, I can make electrons want to move, and that's electricity. Yes?
When you have that battery right there, if you put your finger across the top of it, is the reason it doesn't electrocute?
My finger's not very good at conducting, but you know what? You want to do this? You want to put your tongue on this? If you've never done that, you should do it at least once in your life. Get a brand new 9-volt battery, and you can touch it all you want. But then you put it on your tongue, okay? And you'll be surprised, okay? The tongue being moist, and there's always some kind of like ions in there, it's a pretty good conductor of electricity. I wouldn't leave it on my tongue too long. Yes? Is that what you're asking?
Yes.
Yes. It's pretty good. It's a pretty good. And after you do it, you go, oh, and you'll say, I'll do that again. Because it doesn't really hurt you, but you're really surprised. And, okay, yeah, go ahead, one more.
Have you ever done it with a car battery?
No. Now, the problem with that, I would probably lose part of my tongue, honestly. It would fry it. It would probably fry my tongue, and that piece would eventually fall off, and my tongue would, be like flat across. And yeah, I wouldn't do that.
I hope that your tongue isn't large enough to reach both the positive and negative.
Yeah, that's good. I think he means hook it up to cables or something like that. But yeah, I wouldn't do that. Okay, then the last thing.
Then you might need to.
The last thing you saw was a kind of new something. Even though the first one was in 1935, I'd never heard of it in all of my career until about the last 5 years, and that was an aerogel material. What do you remember about aerogel materials? Not only is it the lightest, quote, lightest or the least dense solid on the planet, big blocks of it may only weigh like 1 gram. It's mainly air, isn't it? But yet it's a solid. But what other properties did it have? I thought it was amazing. Yes?
Well, I have a different question.
Oh, okay. One more and I'll answer that. What was the one property that I thought was just amazing? And NASA uses it for that? Yeah.
It doesn't conduct heat very well because when you heat the bottom of it, it's so difficult for the air molecules to energize the
Right.
above them because there's such a...
So even when I put a pan on the stove, the bottom metal gets energized. But the metal next to metal, it's easy for that energy to transfer from metal to metal and make the next part of the pan hot, the next part of the pan hot, and then the water in the pan hot. See that? But what if you can't get any movement? You can't get any particles to actually move and run into each other, then you won't be able to transfer the heat. So I thought it had great insulating abilities. I thought that was pretty neat. All right, go ahead. Oh, one more thing. I got to move on.
So you know how a lightning strikes
Okay.
and there's ions in the lake, so the water is transmitted. Why will you get electrocuted in there if you're not connected to ground or anything?
I'd be more likely to be electrocuted in the ocean than a lake because there's many more ions there, okay? Also, it has to do with the distance away. If the distance away from you is pretty small, you're going to get hurt. You are going to get hurt. But if it's pretty far away, all that energy is spreading out in every direction. And only a certain amount of it's going to get where your legs are in the lake. I don't know why I have all these stories, but my neighborhood, when I grew up, we placed, I'm in a baby boomer, so there had to be at least 60 kids in a 4-year span in my neighborhood, okay? You want to go out? Hey, hey, you want to play? Want to play baseball? You want to play basketball? Okay? That's how we had to do it, you know. Sometimes you could call them. But anyway, we never had trouble getting some kind of sports game going, okay? And we happened to have a yard that had a side yard. A lot of people didn't have an extra lot, but we did. And that's where we played a lot of baseball and football in our side lot, okay? So we had a baseball game, and we wanted to keep playing, and it might have been a wiffle ball that day. Anyway, and then it started to rain and lightning, and so we went in our garage, opened the garage door, and we'll just stay here till it stops raining. And so we're in the garage, and this one kid, I still remember his name, Michael Kuhn. So Michael Kuhn, he says, "Come on, you guys, what's the matter with you? Come on, let's go out here." So he goes out in the side yard. It's already not filling up. It's got water all over it. "Come on, yeah, he had some of the names, but come on, you guys, come out here." And then I remember a lightning struck. It was pretty close. You knew it's close when you hear the thunder, like right away. It's like boom, boom, like that. Okay, you knew it was pretty close. But I remember watching him go, "Ah!" He goes, "Ah!" like that. And he was in there. It didn't hit him directly, but it hit there and traveled through the water in the lot. And he was like this, and he came out and he was shaking, and he got started crying. You know, he's a big guy, but not a big guy, but he started crying a little bit. I'm going home. Anyway, I don't know if he didn't get struck exactly, but he got struck close enough that there was enough energy in there to shake him up. And so anyway, I think it's distance. That's my opinion. It's how far away are you, and how much does it spread out throughout the whole ocean or lake. But if you're close to it, and the lake's going to have less ions, but it's got a good amount. And I would say if you're pretty close, you will get shocked. The ions tend to be, they seem to be able to carry a charge from one place to another. And that's a good question. What makes ions have the ability to carry a charge? Ions are charged, aren't they? So do they carry extra charge on their charge? That's a good question. But it is a fact that it has ions in it, will carry a charge. It's called an electrolyte. Electrolyte's any kind of solution that contains ions that conducts electricity. All right, I'm going to move on now. Today, I'd like to tell you, I think I mentioned this on Wednesday, we'll have our test. It's actually a mini test. We have another mini test. This is probably around 90 points. And the good news is that a lot of the questions have to do with vocabulary words. So if you think about the vocabulary words in the chapter, I also had given you a packet. I have one here. Remember the packet had a practice test on it? Here it is. Everybody get that? Okay, now I know you have other work to do for this chapter, but maybe before you took the test, you might at least try those pages, and those are the answers to it. So that'll remind you about I think this whole first page is vocabulary words like that. Now, the parts that are not vocabulary words have to do a little bit of mathematics. We already did something a little bit with direct proportionalities, inverse proportionalities, and today we're going to get into Hooke's law, and we'll be doing that. All right, Owen, real quickly, I got to get going.
When is all the packet work due?
Well, it'd be on Wednesday because it's always due on the day of the test. So I would say if you haven't done anything this week, you need to do a little bit tonight and say, well, I can at least read that chapter and maybe do the drawings. I could do that. That's out of the way. I think you'll find the questions go a little faster than you think. You'll be able to answer the questions at a pretty good pace. Well, first thing I'd like to show you that's kind of new material is right here on this page. And let me turn the camera on. Whoops. Darn it. Okay, there. Oops. Okay. Sorry. Okay. We're going to know a little bit about density. And the one thing I didn't get to do yesterday, I thought I was going to get, is we talked about the super dense materials and then these materials. And one of them that kind of stands out, most of you had probably touched lead somewhere, maybe a lead weight or something like that. How about steel? I bet you maybe picked up a piece of steel maybe. So those are kind of heavy for their size. What I'm going to show you today, and I'd like to please, if you're not willing to follow my directions, I don't want you to do it. But I want to show you this stuff right here, okay? First of all, let me preface this by saying that mercury has been around for a long time, and it is an element on the periodic table. It's actually the only metal that is a liquid at room temperature. And so I'm going to show you some of this. Now, in the past, you could do lots of things with mercury. You could even put it in a beaker if kids want to put their hands in it, but that's long gone. There's enough press, public opinion about mercury that I have to be a lot more constrained. So the mercury is going to be in a sealed bottle, okay? You can look at it, but it's not going to be exposed. I'm not going to let you open it up. And I have a little test tube of it if you want to just kind of watch it go back and forth. And I have a little bottle of it, and I'll show you what I want you to do with it. But if you're willing to follow my directions, I'll let you do that. I've actually touched mercury a lot. I haven't, that's why I'm so weird. But no, I think what happened though, the metal mercury itself really wants to attract itself to mercury. So I don't see a huge amount of danger there. What I wouldn't want to do would be to try to heat mercury or vaporize it. Vaporized mercury in my system would not be good. That could be bad for me. Now, on the other hand, I don't know if you knew this, but every one of those light bulbs in the gym, you know why they're so bright? They're mercury vapor lights. So that's why they have a little cage around them, because they don't really want people breaking those bulbs, because then they're going to release mercury vapor. So it's it's at a very low pressure bulb. It has vaporized mercury in it. That's how you get those really bright lights. Now, the thing I think happens though, when you look at environmental issues, mercury always comes up. And they talk about mercury in the environment. But if I were to dump this mercury, I wouldn't want to dump it in a stream, but it would sort of stay there. And even if a lot of water came, it would move a little bit. But it would try to stay by itself. It might get broken up into little pieces. That wouldn't be as dangerous. But a lot of places in the environment have these bacteria that are able to take metallic mercury and put it into a compound, like mercury chloride. Well, what's dangerous about a mercury compound? Many of them are water-soluble. Okay, so what if you have a water-soluble mercury compound? It doesn't look like mercury, but it's water-soluble. Now what happens? Now, every living thing that takes water in can take in a water-soluble compound. And now these mercury ions, the mercury ions are all over your body, and that does tend to mess you up. It does mess up nerve cells. That's your brain also. So I don't have any of that here. I don't have any mercury, soluble mercury, and like that. So all I'm asking you to do is, I'm going to put this back here. The directions are kind of simple. I'll keep it in the tub, okay? And if you want to look at this is some mercury that I put in a test tube for you. And you can see why forever and ever it was called Quicksilver, because it's pretty fast. Matter of fact, if I put it on a table and you try to catch it, you won't be able to catch it. It's too fast. But what happens is it's hard to catch it. So it's called Quicksilver, and that's mercury. Used to be every thermometer was made of mercury, and when I went to the doctor, on the wall they had a sphygmomanometer. That's for blood pressure. That was always a little mercury bar would go up, and then what happened is bad press, mercury, bad. What are you gonna do? Hey, there's mercury in this room. I went out here. Okay, so then they had to take those down, and now they replaced it. Good news, they had a digital replacement. See that? Now, what the hospital had to do, or the doctor's office, they had to get rid of the mercury the right way. And one of the right ways is to pay a company a lot of money, and they would take care of the mercury for you. That was a lot of money. Or, in my case, over 30 years ago, somebody wanted to get rid of it, and he was one of the parents, and one of my students says, "You want some mercury?" I said, "Okay." And so he got rid of a good amount of mercury by giving it to me. Okay. So anyway, that's how I got it. And by the way, another thing happened in dentistry. I don't know if you know this, but when you have a filling and it looks silver, and some of your parents might have silver fillings or grandparents, that is an alloy of mercury. It's called amalgam. And it is mercury and another metal in there. And even though the studies have never shown any mercury being able to leak out of the amalgam because of the bad press. Any of you have fillings now? And you have fillings that are, what color are they?
It's white.
White? Okay, so they stopped using the amalgam now because a lot of people act like, I'm not putting mercury in my mouth. Yeah, but the science shows that it doesn't leak out. I don't mind, it doesn't matter to me. So the dentist just said, okay, we'll switch to something else. The amalgam used to last 15 years, these only last 10. So you probably have to have it replaced here more often. But you don't have amalgam. Yes?
So you seem incredibly superstitious about, not superstitious, but you think that like the effects of mercury and the risk is just completely bogus?
No, not at all. I already told you that I'm not even gonna open it. I don't want mercury vapors. Now, mercury hangs onto itself so much, the chance of it evaporating is very, very tiny. And I know the science, I even talked to some dentists, the science of mercury coming out of amalgam is essentially zero. But there's enough people who believe that if you look at mercury, something's gonna happen to you. So if you don't even wanna come up to this stuff, you don't have to, but I'm not gonna try to put anybody in danger. And I'm not saying that there isn't danger with mercury. I already talked about mercury compounds. They could be very bad in the neighborhood, in the environment. Yeah, very bad. Mercury vapor, very bad. All right, so anyway, what we'll do is, you can look at this when you go back there, and then what I'd like to do then is, on this one, here's a bottle, it's not very big, but if you want to try a little challenge, take this finger and this thumb and pick it up. And you'll say, well, if that was made out of water, that would be really easy to pick it up, and then and I'd like to ask you to not pick it up any higher than about this, okay? So I got a little foam down there, and if something happens, it'll hit the foam, get that? And if something happens there, it'll stay in the tub. So I'm trying to keep it as safe as I can here. All right, so anyway, I'm gonna put this back here, and if you're in the first row, and then after that first row gets done, the second row. But again, don't lift it up any higher, don't make it not be over the tub at any time. So if anybody wants to go there, you can, and if not, we'll go to the next row. And let's just have one person at a time, though. All right. Now, let's look up here, and I'm going to show you a couple of vocabulary words from the chapter. Is that what you expected? That's pretty heavy for its size. It's very heavy for its size. That's a density of around 13.6. All right. Anyway, let's look up here, and what I'm going to do is a couple of vocabulary words. I'll show you. Everybody knows what density is. All right. That's good, but why would the author put two more words on this same page, and they're called weight density and specific gravity? Okay, here's my opinion on that. I believe that there are still people in the United States, engineers that are as old as me maybe, and they probably are still using weight density. Density is mass per volume, but I think there are engineers that still might use pounds per gallon. And that would be called weight density. You get that? Now, I think there are still some people that probably use it. I don't know why, because this author, this is a fairly recent edition within the last 5 years. And so he thought people are still using that word. Now, so that's a minor word. Weight density is simply weight per volume instead of mass per volume. See that? Now, next. This one, I do have a personal story of this one. Specific gravity, if you become a geologist or if you become a gemologist, you're a diamonds, rubies, whatever, if you deal with precious stones, you will see the word specific gravity a lot, okay? Because the people before them used the word, the people before them used the word. So this is a true story for me. When I first started teaching, I remember seeing density, and the density of a material was like 3.1 grams per cubic centimeter. And then I look up in a book, like a geology book, and it said the specific gravity was 3.1. Well, again, when I first started, I really didn't understand what was different about them. So I remember teaching, well, it's really the same thing. So what is different about density and specific gravity? So if you become a geologist and you find the specific gravity of a rock is 3.5, what does that mean? Yes?
It means that if you had a bucket of water that was the exact same volume as the rock, then the rock's weight would be 3 times that of the water's weight.
Okay, or another way of saying that is the density of that rock is 3.5 times more than the density of water. And so let's take a look at this right here. Density is let's say it's 3.1 grams per cubic centimeter. Now, what I understood, and I figured this out after a couple of years. I did not figure it out right away, but after a couple of years, I figured it out. Not too high there.
Hey, sir, are you kidding me?
Everybody,
That looked pretty high,
all right, look
dude.
right here.
Come on.
All right, now, I figured out why this, I used to say they're the same, but this one has units and this does not have units. Notice that? So, does anybody happen to know what the density of water is?
One. Well,
No,
it's
I mean in the English system.
1 gram per cubic.
No grams in the English system.
What was that?
What's the density of water in the English system?
1.
No, that's metric.
Nothing. Let me do some quick
No, no,
math.
it's-
Wait, Mr. Petey.
Well, what I'm trying to say is, it's a number that I was never even taught. And so, but at one time though, there was the density of water, and it was in the English system. Let's just make up a number. Let's just say it was 8. Okay? 8, whatever it was, units. And then I find the density of water. What the geologists want to know was, how many times more dense than water were you? And in the English system, let's say the number is 8, and then your density in the English system was 14. Not 14, 16. Let's say it's 16, okay? Okay, so what is your specific gravity? 2. You are twice as dense as water. You're 8, you're 16. All right? You're twice as dense as water, and that's what they wrote down, and that's why the units always canceled out. This is how many times more dense than water. Now, what I didn't understand when I first started teaching was these numbers were always the same. Well, that's because before the metric system, this is what they used. How many times more dense than water? But once we started using the metric system, what was the density of water? 1. So if your density was 3.1 and the density of water was 1, how many times more dense than 1 are you? 3.1. And that's the story about why specific gravity has no units, but it has the same number because the density of water in the metric system was 1. But before that, it wasn't 1. And people still want to know how many times more dense than water you were. All right, let's go to the next page. This one, the next part of this chapter talks about a property of solids like this rubber band. Whether or not you are crystalline or not, you could have another property called elasticity. And elasticity, I'll tell you the fancy definition. It's it says here, a body's elasticity describes how much it changes shape when a deforming force acts on it, and how well it returns to its original shape when the deforming force is removed. Here we go. There's an object. I'm going to apply a force, and it does deform the shape. It changed the shape, didn't it? Now, what's the tendency when I remove the force to come back to its original shape? That's a lot. This would be called a very elastic material, wouldn't it? What you think you'll be shocked is, what is one of the most elastic materials that we have on the planet, and we use it all the time for elastic materials? Rubber is one of them, There's another one that might surprise you.
Air.
I will say air does, I like that. Air does have a certain amount of elasticity to it. You can change its shape, and it has a tendency, I like that. So that's kind of an unusual one. There's another one. It's a solid. If I say the word steel, you probably don't think about elasticity, do you? Steel's like solid, isn't it? But what do we make springs out of? Steel. Now, the different kinds of springs, one kind of spring might look like this, okay? It's a coil spring. You can have a coil spring, and I think you've seen little springs, and my car has some coil springs on it for big weights. There's also some cars have plates of steel that are kind of bracketed together, and they act like springs. And you can go like this too. Okay, and then they bend, they come back. They bend, they come back. So some cars have what they call leaf springs. Leaf springs. These are coil springs. So steel is actually one of the most elastic materials we know of. I've actually seen I don't know who decided to make this, but I've seen glass springs. Really delicate, but they actually do like that. Now, I'm not sure. I'd have to look up who wants to use glass springs. I'm not sure. They wouldn't rust, but I have to be careful about, vibrations and things like that. Well, anyway, what we see here is this next picture. And even though I am semi-postponing some labs a little bit, I do want you to do them. You're going to do a lab like this. It's called Hooke's Law. Now, if you become an engineer, you'll see that Hooke's Law goes way beyond this picture, but I'm at least going to show you what Hooke's Law is. Robert Hooke, his name is in every physics book, engineering, but it's also in biology books. That's interesting. Robert Hooke, when they figured out how microscopes are made, he made a lot of different microscopes. And then he also wanted to look at all kinds of things under the microscope. You probably remember one time I don't know why he would do this, he took the bark of a certain kind of an oak tree. It was called a cork oak tree. And guess what cork oak trees you can make out of it? Cork. Okay, that's where corks come from wine bottles. They come from trees, the bark of trees. Anyway, so for whatever reason, he wanted to know, if I cut a really, really thin piece of cork and look under a microscope, I wonder what it would look like. And then this is that famous drawing you might have seen in your biology book where it looked like something like a bunch of rooms, a bunch of square rooms right next to each other. That reminded him, and we'd gone to a monastery, they had rooms there, square room, and guess what they call a series of square rooms? We also have them in prisons. Cells. And that's the word cells, it had to do with a room, and he said, they look like cells to me. And that's why his name is in a biology book, because he first used the word cell. Now, if I were your biology teacher, I would have taught you that what he was really looking at is the dead part of the cell, the cell wall. The living cell is long gone. It's long gone. Just like if a clam dies, the living part of the clam is long gone. You can still see the shell, can't you? If you saw a human skeleton, that's what a human looks like? No. That's when all the good living tissue dies, that's what's left behind. And that's what this is too. All the living cork cells are gone, but they left behind a skeleton. And we still call those cells today. Yes?
The density of water in imperial units is 0.578.
Wait, I'm on to that.
centimeter.
What is it?
0.578 ounces per cubic inches per cubic inch.
Okay. Now, you can see that no one ever actually taught me that, but at one time, if that was accepted as the density of water, they still want to know how many times more dense than water you were. So if you're in the English system, let's say it came out to around 1.5, then you would divide those and get a number somewhere close to 3, wouldn't you? All right, I'm gonna, if you put that on a piece of paper and put your name on it, I'll give you credit for that. Okay. All right, so give it to me at the end of the period, okay? So anyway, that's not even an easy number to remember, is it? The density is 0.578 ounces per cubic inch. Whoa, that's weird. But you could still do this, couldn't you? You're in ounces per square cubic inch. I'm in ounces per cubic. Water is 2, and so are you. And so I still cancel out the units, and I get 3.1. Okay, here we go. Now, so let's take a look at Hooke's law, and let me tell you what Hooke's law is. Here's Hooke's law. F squiggly line delta x. That's Hooke's law. F squiggly line delta x. Some books do it like this. F, funny looking, almost like a Christian symbol. F, something symbol, delta x. Now, what does that mean? What are the two variables in Hooke's law?
Change.
What is it?
Change.
One more time.
Change.
Change in what?
In
What's delta x stand for? Matter of fact, some books might say, F squiggly line delta L.
length.
Is it length or change in length?
Change in length.
See that? Everybody got that? So, if we did an experiment, and you're going to do one of these, okay? I want you to imagine you have a spring, and then you're going to put a weight on it, and you got to figure out how much it's stretched. Another way of saying it is stretching amount. Delta x could be the amount of stretching. And what he found out is F squiggly line stretching. That means that force is directly proportional to the amount of stretch. Now, one more time, let's try this again. If I did a graph of these, what would the graph look like?
Straight line.
And we know that all direct proportionals are linear that go through 0, 0. I already know the graph's going to look like that. But now what I want to do is I want to turn this into an equation. Let's go back here. Here's my graph, mass, volume. Mass, squiggly line volume. Mass and volume are directly proportional to each other. But how do I change that into an equation with an equal sign? Mass does not equal volume. Mass does not equal volume, but mass will equal volume if you multiply it by something else, right? And that's your math thing. Y equals mx plus b. If it goes through 0, 0, there is no plus b. Y equals mx. M equals the slope times v. So look right here. That's what we had here. M equals the slope times v. That's where the equation came from. That's how you change a proportionality into an equation. Now, where did I get this? They have a fancy name for that. It's called the constant of proportionality. It's what makes the equation work. Look down here. True or false? Circumference equals diameter. That's false. True or false? Circumference is directly proportional to diameter. That's true. True or false? Circumference equals diameter if you multiply by the constant of proportionality. In this case, it's pi. In this case, what was the constant of proportionality here? What was the slope of this line equal to? Somebody said it. Density. Well, guess what? All right, M equals density times volume. That's how you turn an experiment into an equation. So let's go over here. Ready? Stretching is directly proportional to the force. All right, okay. Now, but I can't, I should have redrawn, let me redraw this, sorry. Let me do it this way. So delta x equals F times something. What is this going to be? We know they're directly proportional to each other, but how do I turn this into an equation? Y equals mx. Y equals mx. And where do I get this right here? Look, everybody, look at me. Come on. Where do I get this right here? Where do I get that constant? Okay, I'm sorry. I'm sorry. That's my fault. These are directly proportional to each other, but if I want to turn it into an equation, y equals mx. Where do I get the constant from?
Slope.
The slope. Now, it just so happens this is going to give me like centimeters per Newton. So this would be something like so many centimeters per Newton. Now, if I owned a spring company and I wanted people to buy my springs, I would have a part of my company that did all the testing. I have a part of the company that makes the springs. I would have a part of the company that tests the springs. Because if I offer people these springs and I make model A55 and some of the A55s stretch this much per Newton and some of them stretch a different amount, I will be out of business very quickly. They would expect my company to the A55 model to have a certain spring constant. The engineers would say, I have this thing, and I need a spring that will stretch exactly this many centimeters per Newton of force on it. Do you have it? Oh, that's my model B5. That's the B5 because it has a spring constant that's exactly what you want. Okay, I'll take 100,000 of those springs. I'd also have part of the company that would be called quality control. I'm making a lot of springs. I'm making 1,000 an hour, okay? Somebody would take a random 20. Take a random 20 of those springs. Take it to a special room. Do something like that. Hang a weight on there and see how much they stretch.
How would you get those 20 random springs?
Okay, if it's coming off the assembly line, all right, good question. If they're coming off the assembly line and they go into a basket, I might just pick them out of there. If you're a stats person, that's a great question. How do I know that I'm getting a random sample? So maybe in an hour's time, I take some in the first 5 minutes, some in the middle 5 minutes, and some in the end. So you're right. That's a great question. I want to make sure I get a random sample. Okay, hang on. Okay, hang on. Shh. All right. So anyway, I want to make sure those springs have the same spring constant. Got it? The worst thing in the world, let's say a manufacturer makes handguns, and they're going to make, 50,000 of these handguns, 100,000. And the engineers show them, I want the trigger, I want this much force to be applied before that hammer comes down. You see that? Now, if I get a batch of springs and they're not identical, then you'll have some guns that might go off what they call early or hair trigger. And that would be, you could actually kill somebody. That's serious stuff. It's not just being in class. That's serious. If you know you're selling springs to a gun company, you better make sure that all of them are the same. Okay, if you are a tennis player and you go and buy new tennis balls, you expect them to have a certain kind of a bounce, don't you? And have you ever bought a can that just didn't bounce like it should? And if you haven't, here's what happens. That tennis company will do the same thing, and they will have a room where a mechanical room or something drops the ball, and they'll have a slow-mo video, and they'll say it went up this high, and the index of bounciness has to be this number between here and here, and if it's not, we're not going to sell those tennis balls. All right, so I want to show you, darn it. Okay, I want to show you one more thing before you leave, okay? When you do this experiment, this is the hardest question I've asked all day. When you do this experiment on Hooke's Law, I'll give you two different kinds of springs. One that's easy to stretch and one that's not so easy. And you'll get two different spring constants. Now here's my question. What if you did the lab and you knew you were supposed to get this, but you got this? What do you think they did wrong? Because they had a linear relationship, but it didn't go anywhere close to 0, 0. What's your best guess as to what they did wrong? Yes?
They either A, used different springs, did different springs, so there's a different starting point, or they used a different weight.
They probably didn't use different springs during the whole experiment. You know why? Because it came out to be very linear. It was probably the same spring. I'll give you a clue. When the force was 0, they recorded it had a stretching amount. What do you think? What did they do wrong? The other class had 4 or 5 guesses, so I know you're capable. Yes.
Maybe they could have held it like this.
Okay. it might have something to do with that. When you said I have no force on it, but it had stretching amount, what if they thought it was the length of the spring was a variable? What if they thought the length of the spring was a variable, not the lengthening? Then, with no, wait a minute,
Attention
wait a minute.
CR students.
With
Student
no force on
drivers
it,
may now be
it would
dismissed.
still have a
Class will
number, wouldn't
begin
it?
in 5 minutes.
So wait, wait a minute,
Please
wait,
drive to your
hang on,
classroom
just give me 1 minute,
until
or less,
class will
less than a
begin.
minute.
Thank you.
What you need to do is measure the length of the spring with nothing on it. Then, let's say that's 4 centimeters. Then you put your weight on it, and let's say it goes to 4.5 centimeters. What are you gonna record in your data table? 4.5? 0.5. You're gonna zero it out. And if they didn't zero out the length of the spring, then that would make them cut through the y-axis there like that. Okay, thank you very much.